It will also be important to verify the solutions for the problems that we've just seen involving flow to streams, either steady flow or transient flow. And so here are the analytical solutions for those cases. The steady state head distribution between streams, where the streams are at equal head, are given by this expression here. And here are some examples of what the profiles look like from this equation. If the heads in the streams are at different magnitudes, then you have a little bit different expression here, and this is what the head profiles look like. So for our case, the heads are equal, and we can use this expression. And so what we need to do is put this expression into Comsol so we can use it. While we're here in PowerPoint, though, let's take a look at the expression for the transient problem. In order to simulate the transient heads, we need to have an analysis that simulates the step increase in the hydraulic head in one of the streams, and then this wave that propagates across. And so this is the solution. It's 1 minus the error function of this argument here. This is a classic solution for propagation of a diffusive wave. Now, I should also mention, though, that the analysis that we conducted for the transient problem started with the heads at steady state. So we start with this ridge, and then we have a step increase, just as if one of the streams raised in elevation. And so what we need to do is take this transient analysis here and superimpose it onto the steady state analysis when we do the verification. So here's the numerical analysis that we conducted using one of the previous videos, and here are the profiles of hydraulic head for the transient case. So this is what we'll ultimately try to verify. Initially, though, let's go to the steady state profile, and the verification is done here. So the green is the analytical expression that we just saw, and the points are the numerical. And so let me show you how I did this. All of this stuff, the setup of the analysis, is done the way we saw in one of the previous videos. And so what I did for this case is added in the global definitions region, the analytical solutions that we saw in PowerPoint. So I did this by right-clicking and selecting Functions Analytic. And so if I take a look at this, this is the function. So this function here is the same function that we saw in the PowerPoint expression. Recharge, that's L, is the distance between the streams, hydraulic conductivity, and so forth. So I type this in here under the expression, and then these are the arguments. And so these are the variables that we'll need to give this function when we call it from down within the program. Now, one thing that I did was to open up properties, and the properties give you a place for putting in comments. So I wrote in a comment that said what this function does. It's the steady state head profile, so-and-so, and it gives the what the parameters are. I also put my initials here in as the authors, and I changed the name so that it was something that was relevant to this particular problem. One of the things that you notice is that Comsol gives these things names, but they're just generic names, and it sometimes is hard to keep track of what they indicate. So I've specified what this name is. So this is the analytical case, and what I did then was to come down here, and in order to implement this, you type the name of the function, and then it has a list of parameters that we saw up there in the up here, and then what you do is type in the numbers, or you can use the appropriate variables to basically put the values, pass the values from the analysis that you've created here in the model into this function. This is really just the way that you would use a function in any other programming language. Okay, so the list here of these numbers is the same as the argument list here. So when we do that, we create these points over here. And what I did was to set this up so that the the analytical expression is the green line. The analytical expression is a continuous function of x, and so I plot it here as a continuous line. The numerical results I plot here as these points, and I did that by turning the line off right here, and then boosting the size of the points here. We might want to boost them a little bit more. Okay, so we can see that the fit is really quite good. We could calculate the relative error, but it looks really pretty good. In many cases, what we do is to do the verification analysis just to confirm that we're on track, that the numerical analysis is working properly, and that we understand it. And indeed, this is close enough for that purpose. Okay, so let's take a look at the transient analysis. Here are the results. Again, the points are numerical and the lines are the analytic expressions. And you can see that they're quite good. This plot looks a bit different, though, than this plot. And so let me show you some of the differences. What I did here was to plot the results over a cut line that I defined up here. And we used that cut line previously. It's called Profiles Transient. And I set it up so that I defined the transient profiles out here, and then the time selection was interpolated, and I used these 5 different times. Well, I guess they're 4 different times. Okay, and then when I made the actual plots, these two define the plots, what I did was to use the data set from the parent for this plot and from this plot. And the reason for that is because then when I set the times here in the parent, both of these will use the same times. If I set it up so that I use profiles transient here and times, I would have to make sure that these times that I specified here were the same for the numerical and analytical. And that could be done, but by using this parent-daughter relationship between the plots, it's possible to coordinate that in a much easier way. Okay, so that's one thing. The other thing is that the analytical results here use 2 different functions. It uses this function here, which is the same analytical expression that we use for steady state, HSS, and then a list of parameters. And then it adds to that the transient function. Okay, so this is the superposition process where we take the transient analysis and add to it the steady state analysis. And this the superposition is required to get the results shown here. So let's take a look at HTrans. That expression right there, that name of the function shows up right here. So you can see HTrans and HSS for steady state, that shows up right there. So this is the name of this particular definition, but that in the parentheses is the name of the function that's defined here. So if we go to analytic transient, we can see there's the error function and the arguments for the error function. Comsol just knows what the error function is, so we can just use ERF. And this expression is really the same that we saw on PowerPoint, with one exception. And that exception is shown here. This is 9800 times SS. When we look over here in PowerPoint, this is written assuming that the units of K and SS are the same. That in this case, K would be in units of length per time, and specific storage would be in units of 1/length. Well, in fact, specific storage is set up in several different ways. And in Comsol, if we look at the transient analysis here, if we look, let's see, up here in the model and expand out and go here to the storage model where the transient terms are given, we see here this is S, this is the specific storage, or this is what we're using as the specific storage, and it's in units of 1/pressure instead of 1/pressure head. And so that's just a difference in the convention, and because of that we have to convert this term here from units of 1/pressure to units of 1/pressure head. And the conversion is done through the unit weight of water, which is 9800. And what I did was just put that 9800 right here in the expression. So that's just a little twist that comes out of how these different terms are defined, but it's an important one to point out because because you have to know that you have to get the units right in order for this expression to work out. So keep this in mind as you set up additional analytical expressions.